Okay, we're starting chapter 2 today. Chapter 2 is the chemical contents of life, which, chemistry is kind of my thing, so this is going to be a fun chapter. Okay, why do you say the chemistry? We're studying biology. Well, biology is the study of life, but anytime you study living organisms, they interact with their environment. And because they interact with their environment, you have to be subject to the basic laws of physics and chemistry. It's not like, this entity is over here and this and that. They all intermingle. So that's why there's this connection with all the other sciences when you're studying biology. An example is ants. When ants feel threatened, they can send out these little strands of formic acid, and the formic acid protects them against predators. It also is kind of like their own little Clorox wipes. It stops microbial parasites. It kills them. So they have, they're using chemistry to protect a living organism, the ants. And here's the ants throwing out their little formic acid. Okay. So when we study chemistry, we study matter. Matter is anything that has mass and takes up space. Okay. Organisms are made up of matter. Really living things are just a bunch of chemicals kind of all mixed up together with, similar characteristics or similar jobs to do. Okay, so matter is anything that has mass and takes up space. All right, sometimes I'll ask people, okay, tell me something that isn't matter. And a lot of people will say air. Well, you can feel air, and you're like, no, you can't. Walk outside on a windy day. Yes, you can feel air. So air is matter. Okay, things that aren't matter would be like energy, light, things like that. But in general, pretty much almost everything is matter. Okay, so when we're talking about matter, matter is made up of elements. There's 118 elements. If you want to know what they are, they're on the periodic table. I'm sure you guys have used a periodic table before. An element is the smallest you get. You can't break it down anymore. If you take a compound, you can break that down into elements. But once you get to the element, you're done. That's as low as you go. Okay. So a compound is two or more elements that are combined in a fixed ratio. By that, I mean like water's H2O. There's always 2 hydrogen for 1 oxygen. If you mess with that ratio, then you don't have water anymore. You have a different substance with different properties. So a compound always has the same elements in the same ratio. Okay, you can come up with a lot of different carbon compounds. You can have CH4, you can have C2H6, you can have C3H8. You keep going in order. They're just made out of carbon and hydrogen, but you change the ratio and you've got different substance. CH4 is methane, natural gas. Okay, C2H6 is ethane. Okay, ethane is another type of gas, but not natural gas. It's not something we use a lot of. C3H8 is propane. Okay, up here we use a lot of propane. Where I came from in the cities, we used a lot of natural gas. They're different compounds with different characteristics. Okay, so a compound is different from the elements it comes from as well. And here's an example. Here's sodium, which is a really, really soft metal. You can take tweezers and take off a piece of sodium. It's really soft. Here's chlorine. I'm sure most of you guys know what chlorine is, that greenish gas. It's a great disinfectant. It's the one that burns your eyes when you swim in the pool. If you take some of this and put it in here, they will react violently and they'll produce salt. And I'm talking about the stuff you put on your food. Okay, so these two are way different than the stuff it comes from. Okay, so when we're talking about the elements of life, 96% of all living things is made out of carbon, hydrogen, oxygen, and nitrogen. Okay, and you're saying, well, like, aren't we made up of water? Well, water's in there. Hydrogen and oxygen make up water, so okay, they're in there as well. But 96% of all our parts, or all the stuff inside of us, is those 4 elements, excuse me. Okay, then there's other essential elements. There's a whole kinds of other elements involved, but most of them are just those 4. Okay, the other 4%, calcium, phosphorus, potassium, sulfur, and then there's trace elements. Okay, we only need a little tiny bit of trace elements like iron and iodine and things like that. Okay, so those are the elements, but there are 92 elements that we use, but the top 4, the ones that make up most of us: carbon, hydrogen, oxygen, and nitrogen. And actually, to be considered alive, you have to have carbon. Okay, here's another chart that explains it maybe a little bit better. And you can see oxygen's number 1 here, 65%. And a big part of that, and this is by body mass. But a big part of these two together is your water. I mean, we're 70% water, so that's a big part of it. But you can see oxygen, carbon, hydrogen, nitrogen. They make up most of us. Then down here we have our other elements that we have a little bit of: calcium and phosphorus in our bones, potassium, sulfur. Sulfur you'll find in like DNA, sodium, chlorine. Those are electrolytes you find in our blood, things like that. And then the trace elements are down here. Okay, we need a little bit of chromium. We need a little bit of copper, fluorine, iodine. I know if we don't have enough iodine in our, we get that big goiter thing, you know. Iron, we need iron for our blood so that we can carry oxygen. If we don't have enough iron, we get anemic, things like that. But these are the elements that are found in the human body. Okay. All right. So we can also, if we have too much of it, or if we get the wrong trace element, we can have some issues. And there's an example with arsenic. Arsenic used to be the way that women used to kill their husbands. Arsenic is found in like rat poison and, things like that. So they'd sprinkle a little in with the evening meal. And next thing you know, he'd die. And they'd be like, oh, he had the bad flu. And at the time they were doing this, that wasn't that uncommon for people to die from influenza and stomach ailments or whatever. But, they kind of got onto that. And one of the ways that arsenic will build up in your system, your body won't get rid of it. If somebody dies and they suspect it was arsenic poison, all they have to do is test their hair, because your arsenic will be stored in your hair. And they can actually tell how many times you've been poisoned by it'll deposit in your hair. So that part's kind of cool. But it's very, very toxic. And if you get poisoned by arsenic, you're going to die. They can't do that anymore because, they're onto it. But that used to be a big way. Sorry, ladies, you're going to have to come up with some other way if you want to kill your husbands. All right. So when we talk about the structure of atoms, if you remember when you talked about solids, liquids, and gases when you were in elementary school, they always said it was the particles. If they're really close, it's a solid. If they spread out a little, it's a liquid. They're way far apart, it's gas. Well, when they're talking about particles, they're talking about atoms or molecules if you're talking about a compound. But an atom is the smallest unit of matter. That's as small as you get, okay? It will have the properties of its element. And every element's atoms have the same properties. But if you take two different atoms, if you take a hydrogen atom and an oxygen atom, they won't be the same, okay? Their properties will be different. But all hydrogen atoms have the same properties. All oxygen atoms have the same properties. Okay? Okay. In an atom, though, you actually have smaller parts. Now, they don't exist by themselves, okay? But these make up atoms. There's three parts, okay? The subatomic particles, you have neutrons and protons, which are found in the middle of an atom. They make up the nucleus, okay? A neutron doesn't have a charge. And neutrons can vary. Okay, because neutrons just make it a little heavier, a little lighter, kind of like us during the holidays. Protons have a positive charge. So overall, the nucleus does have a positive charge. So you have this positive charge in the middle. That's why the electrons who are on the outside that orbit around the middle stay there, because they're attracted to that middle part. So the three subatomic particles in an atom are neutrons, protons, and electrons. These two guys make up the mass. When you add these together, you get the mass. And these two guys have, this has the positive, this has the negative. So if you have 20 protons, you have 20 electrons because you want them to equal each other. So overall, you don't have a charge. Okay? So neutrons and protons, like I said, are in the nucleus. And then the electrons form a cloud around the nucleus. You'll find two electrons in that cloud. It's hard to nail down electrons because they're really, really, really fast. Every time you figure out where they're at, they've moved. Okay? Here's an example so you can see a better idea. Here's my nucleus. You can see I have my two pink protons and I have my two brown neutrons. So this is the nucleus, okay? And then out here in this cloud area, you will find two electrons. This is helium because helium is the second element, okay? Or you can draw it like this if you want. But it looks really more like this. It's not like a set orbit. It's an area that you find them in, but it's not this defined. Okay, so when you're looking at atoms, if you look at a periodic table, you've got all the elements listed, and above their symbol, you'll have a number, and they go in order. So you start with hydrogen, then go to helium and lithium and so on, and the number above them, 1, 2, 3, 4, 5, that's called their atomic number. It is the number of protons. Okay, if you change that number, if you change the number of protons, you do not have the same element. So the number of protons never, ever, 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 ever changes. Okay, if you change the number of protons, it's not the same element. You can change the number of electrons. You can change the number of neutrons, but you can never change the number of protons, because if you change the number of protons, you have a different element. Okay, if you want to figure out the mass of an atom, what you do is you add the protons and the neutrons together. Okay, not the electrons. The electrons are too tiny. They don't even figure into the mass because they're just too tiny. Okay, so the atomic mass is usually on the bottom. Like you'll have the atomic number, the symbol, the name, and then a number. That's the atomic mass. And it is an approximate of the mass number because you have to figure it in all what they call the isotopes. And so the isotopes, moving on to the next slide. How was that a good lead in, right? What an isotope is when you have different number of neutrons. Okay, you can change the number of neutrons because they don't have a charge, so they don't affect it in that way. So every element has at least 2 isotopes. And what it means is, like, you can have hydrogen with no neutrons, you can have it with 1 neutron, you can have it with 2 neutrons. And what it does, adding those neutrons, is it changes the mass. Excuse me. Isotopes are 2 atoms that have the same number of protons but different number of neutrons. And so that mass number that's written there, that's an average of all those, figuring out the percentage, the relative amount, and so on. So, but anyway, anytime you want to figure out the mass of an atom, you take the number of protons and you take the number of neutrons. If you change the number of neutrons, and you can do that in an atom and still have the same element, it's just heavier or lighter, that's an isotope. Okay, there are radioactive isotopes in the heavier atoms or the elements. They, not so much in the little guys, but when you get to the bigger ones, they have a lot of radioactive isotopes. When they break down, they actually decay and they give off particles. And we use those in medicine quite a bit. Sometimes you'll hear about people have to take in barium, radioactive tracers, and they'll follow. Another one is iodine. They'll give you radioactive iodine, and it can follow certain things through your body because it glows. And so they can take pictures of it and see where it's at. Okay, so they can track atoms through metabolism. They use it. Sometimes they use them to treat diseases too. You know, there's all kinds of things you can do with those radioactive isotopes. Okay, so they use a combination of very sophisticated imaging. This is where you're going to have PET scans. I think they're PET scans, where you're going to take something ahead of time and then they're going to see. When they're testing your thyroid, they use radioactive isotopes quite a bit. Okay, here's a cancerous throat tissue in the thyroid area. So they took something ahead of time and then it gave off a color, and then they knew that they had that issue, so now they got to deal with that. Okay, they also use radioactive decay to date things. Okay, all the radioactive, when they break down, they have what they call a half-life. It's a fixed rate, is when they break down into half of the material they had before. Some things have a half-life of a day. Some have a half-life of an hour. Sometimes the half-life's thousands of years. Like nuclear material, like, you know, plutonium and stuff that they use in nuclear power plants, their half-lives are into the tens of thousands of years. That's why we have that waste when they're done with it forever. Okay, so they like to use radioactive dating. They usually use carbon-14. That's the most common way. And then they'll measure how much carbon-14 is in an object, and then they can trace it back to how old that fossil is or that rock or whatever. That's a lot of the ways that they figured out how old the Earth is, because there was nobody around when the Earth was formed. You know, not anybody that wrote it down in a book or anything. Okay, so half-lives, like I say, it could be seconds, days, to billions of years. It depends on the substance. But the radiometric dating, they use carbon-14 because they got a good handle on that, and they know how to use it to figure out how old things are. Okay, all right, when we're talking about electrons, we better probably quit here because I'm at 14 minutes, so we'll start next time with the energy levels of electrons. So we got the first part of our chapter done. Make sure when you're done watching this that you do the assignment and then move on to the next part of the chapter.